So a few weeks back, this Google research paper drops and just completely blows up the AI hardware world. It promised this revolutionary way to slash the cost of running large language models, and of course, the internet went nuts. But, there's always a but. Beyond the hype, there are some critical details every single engineer needs to understand. So let's dive into what's really going on with TurboQuant.
And look, this wasn't just some dusty paper for academics. No way. The claims were so big, so disruptive, that investors reacted almost immediately. They started questioning the very foundation of major hardware companies. The money people were definitely paying attention, and yeah, they were pretty spooked.
I mean, we're not talking about a tiny blip here. Huge memory chip makers like SK Hynix and Samsung saw their stocks take a real hit, dropping 6% and 5%. The market basically read this paper and thought, uh-oh, does this mean the world is going to need a lot less high-bandwidth memory? The very stuff that's fueling this whole AI boom?
Of course, the internet did what it does best. The community instantly slapped a nickname on it, Pied Piper, from the show Silicon Valley. And while the meme is great, the reality is that the hype is missing three critical things. Three things that any engineer building real production systems has to know before they dive in headfirst.
So here's how we're going to break it all down. We'll start with that hype, then get into the nitty-gritty of how the tech works. After that, we'll hit the production trade-offs, the stuff that really matters, the academic drama, the amazing community response, and we'll wrap it all up with a practical deployment checklist for you and your team.
All right, first up, the Pied Piper hype. Let's really unpack how one single research paper managed to shake up billions of dollars in the market practically overnight.
Okay, so the big problem TurboQuant is trying to solve is something called the KV cache. You can basically think of this as the model's short-term memory. For every single token, and that's pretty much every word or piece of a word, the model stores these little key value pairs. The problem is, as your conversation or document gets longer, this memory usage just explodes. It's a huge cost driver.
Okay, so if that's the massive problem, how does this tech actually fix it? Let's get into the mechanics of how it takes these raw data vectors and crunches them down into a ridiculously small 3-bit package.
And here's the high-level view of the process. The headline here is just, wow, compress that KV cache down to just 3 bits. That means it's 6 times smaller, and it makes the attention mechanism 8 times faster on modern GPUs, all with supposedly 0 loss in model accuracy. Sounds pretty good, right?
So how do they do it? It's a 2-step dance. First, a step called PolarQuant randomly rotates the data. Now that sounds weird, but what it does is force all the data points into a much more uniform, concentrated shape. Think of it like straightening out a tangled mess of yarn before you try to roll it up. It just makes it way easier to compress. Then, the second step, the QSJL transform comes in and uses just one residual bit to correct any tiny errors or bias. Yeah, you heard that right. A single bit to clean up all the mess.
And this chart really tells the story, doesn't it? That red line, that's the nightmare scenario of standard memory growth, just exploding upwards. But look at that green line for TurboQuant. It's almost flat. That's your 6x memory reduction in action. The paper even claims this is getting close to the absolute rock-solid mathematical limit for lossless compression.
Okay, a 6x memory reduction, an 8x speedup. Sounds almost too good to be true, right? Well, that brings us to the big catch. The really critical part for anyone thinking about using this in a real enterprise deployment. The headlines, well, they don't tell you the full story.
Here's the absolute key takeaway. Your workload matters a lot. See, TurboQuant gives you that amazing speed up during the decode stage. That's when the model is generating new words. But it actually adds a little bit of latency overhead during the prefill stage, which is when it first processes your prompt. So, if you're doing stuff like massive RAG pipelines or processing long documents, you're memory bound, and this is a huge win. But if you're running a high-throughput service with tons of short, quick requests, that prefill cost might actually make things slower.
And hey, this isn't just theory. We've got actual numbers. The community-built Turbo ESM implementation measured this overhead. It adds between 21 and 27 milliseconds of latency to that prefill stage for every single request. You can see how, at scale, that could become a real deal breaker for some applications.
So this really boils down to one critical question you have to ask your team. What's the #1 priority for your service? Are you trying to maximize throughput and save on memory, basically cramming more users onto every GPU? Or does your application absolutely require the lowest possible latency on every single call, no exceptions?
Your answer completely changes whether TurboQuant is a brilliant move or a bad one. Now, on top of the technical trade-offs, there's another whole layer to this story that kind of got buried under all the hype. There's an unresolved academic controversy that any serious engineering team needs to know about before they commit to this.
So the authors of an earlier paper called RaBitQ, which also uses this random rotation idea, they've publicly pushed back, hard. They're raising 3 major red flags. First up is attribution. The RaBitQ team says, hey, you didn't properly credit our work on this. Second, the benchmarks. They point to what they call an unfair comparison, pitting a single CPU core against a top-of-the-line A100 GPU. I mean, come on. And third, they say the TurboQuant paper just dismissed their theoretical proofs without providing any evidence to counter them.
Look, don't just take my word for it, or theirs. This is all happening out in the open on the ICLR Open Review Forum. If you're seriously thinking about this for a production system, you have to do your homework. Go read the rebuttal. Understanding the prior art matters, and digging into the benchmark methodology matters even more.
Now, here's where the story gets really interesting. We have this potentially game-changing paper, a brewing controversy, and the kicker? Google didn't ship any official code with it. But as you're about to see, that didn't slow the world down one bit. The open source community simply did not wait around. I mean, we're not talking weeks or months. Within days, developers all over the world started shipping working implementations. We got a Rust library, PyTorch and Triton kernels popped up, there was a port for Apple Silicon, and even a C++ implementation for llama.cpp. The ecosystem just moved light years faster than the original research team.
All right, so let's pull all of this together into something you can actually use. We've gone through the hype, the tech, the catch, and the drama. So now what? Let's build a deployment checklist you can take right back to your team for Q2 planning.
Okay, before you write a single line of code, you need to run through an enterprise risk checklist. First, let's talk technical debt. Are you really ready to bet a production service on community code that has no official support? Second, security. What's your team's process for auditing third-party libraries you pull off the internet? Seriously. And third, vendor dependency. What's your plan if, or when, Google finally releases an official version and it's totally different from the community one you've already built on top of? How painful will that migration be?
Okay, so here it is, your 3-step action plan for Q2. Step 1, run a workload diagnostic. Prove to yourself that you're actually memory-bound and that this tech will provide a real benefit. Step 2, conduct an implementation audit. If you're going to use a community port, pick one, but do it with your eyes wide open about the risks involved. And step 3, perform a methodology review. Go read that RaBitQ rebuttal. Make sure your team is making decisions based on the full, nuanced picture, not just the hype. And really, that's the bottom line here. TurboQuant isn't just hype. The math is solid, and it points to some massive potential efficiency gains. But it is not a silver bullet. The production trade-offs are real, the academic drama is definitely worth watching, and for now, the hard engineering work of vetting, integrating, and maintaining this powerful new tech in a production environment, well, that's all on you.